What are inverse functions? How do we find them? So if we had f of x equals 2x plus 3. Find the inverse. The inverse uses that -1 exponent. So here are your steps. First step, y equals 2x plus 3. First thing you have to do is switch x and y. Second step, solve for y. We got 2y is equal to x minus 3 divided by 2. So my inverse is x minus 3 over 2. So switch x and y. Solve for y, which is now going to be your inverse. So that's how you find it. How do you test inverse functions? To see if they're really inverses. Very good. And what should it equal? Excellent. Very good. Very good. To test to see if your inverse function is really true, you do composite function, and it should equal x. And it has to equal both ways. F of f inverse and f inverse of f. So in our example, we have f of x is equal to 2x plus 3. Our f inverse of x is x minus 3 over 2. So what the first one tells us is we got to take f of f inverse. What that means is we take this function and put it in place of x in the first equation. So we have 2 times x minus 3 over 2 plus 3. The 2's cancel. X minus 3 plus 3. The 3's cancel. It equals x. Check. Then we got to do it the other way. What this one says is f inverse of f of x, which means anywhere you see an x in the inverse, we put f of x in its place. So anywhere you see an x, we put that equation in its place. 2x plus 3 minus 3 over 2. The 3's cancel. 2x over 2. So those are inverses. That's algebra. That's linear equations. Now logarithmic functions. If I had a logarithmic equation, what is its inverse? These are inverses of each other. And there's a whole set of properties that we have in logarithmic or exponential equations and logarithmic equations. For example, if you have a product, log of x times y, what does that equal? Very good. Log x plus log y. If you have a quotient, log of x over y. Very good. If you have an exponential, log of an exponential, what does that equal? Right, because you cannot have exponents that just go in front. Again, these go both directions. We can go this way and we can go backwards. The conversion from logarithmic to exponential. If I give you a logarithmic equation, that equals some number y. The conversion here is I take, because this is called a what? This is called a base. How would you read this statement? Of x equals y. That's how you read. So the base has to remain a base. So what happens here when we convert to exponentials, the base comes over here and pushes up the answer. So we have a to the power y. Since the base is gone, the log disappears. So you have a to the y equals x, which is why you see this is an inverse, because I switch x and y. So log exponentials are inverses of logs and vice versa. There's another property. A to the power log base a of x. What does that equal? Very good. Because if the bases are the same, they cancel each other out. three different scenarios, possibilities we can have here. Log of x, log base a of x, or what's this one called? Natural log, ln x. What makes these things what they are? Was that? What makes them that way is their base. If there's no base, this is what's called a common log, which means that there's automatically a base 10 down there. The reason it's called common because we have a decimal system base 10. So that's what that is already. So if there's nothing there, it's automatically a base 10. If it's an ln, we call this a natural log, which is the log base e of x. So e and ln are inverses of each other. And everything else has to be written that way. In your calculators, you're only going to see two keys. In your calculators, you're only going to see the ln key and the log key. If you're going to try to find the value of log base anything else, we have to use something called the change of base formula. The change of base since our calculators can't handle anything other than e or 10, it's the ratio of whatever you're taking, and then the base will be the other, the denominator. And they're both logs, or they're both going to be ln, because it's the ratio we're looking at, and that'll give us the same ratio, the same value. So far, so good? Derivatives of inverses of differentiable functions. This is important. The function has to be differentiable on the domain in order for it to have an inverse. If it does have an inverse, it's also a continuous function, which means you can find the derivative of that function there, of the inverse function. So let's look at this example. F of x equals x over 2 plus 1. What's the derivative of this function? No. No. What's the derivative of that function? No. Nope. It's not. Okay, I'll give you. It's not negative. The derivative is the same as a what? As the same as a slope. This is a linear equation. Its coefficient is 1. So I can split those. So what's the slope of that equation? 1 over 2. You only take the derivative of x. What's the derivative of x? 1. So it's 1 over 2. It's not a quotient rule. It's not anything. It's just take the derivative of x. It's 1, so it's 1 over 2. This one goes to 0. So let's find the inverse function. So we have y equals x over 2 plus 1. Let's find the inverse. How do we do that? First step. Switch x and y. Solve for y. Subtract 1. So we have x minus 1 equals y over 2. Multiply both sides by 2. So the inverse is 2x minus 2. So the inverse function is 2x minus 2. What is the derivative? Of the inverse function? I'll put it this way, it makes it easier to read. What's the derivative of the inverse function? What's the derivative of that function, ladies and gentlemen? 2. So look at the derivatives of the two functions. What do we notice about them? Not a trick question, it's just observation. What do you see? Not the inverse. Well, obviously f and f inverse, which is derivatives, so there has to be inverses. But look at the values. What do you notice about them? That's not 2. What do you notice about the slope of the function and the slope of the inverse? How are they related? It's 2. This is 1/2. How are they related? Let me make it easier for you. 2 over 1. They're flips of each other. They're reciprocals of each other. This is 2. This is 1/2. If this was 5 over 4, this one would be 4 over 5. They're reciprocals of each other. It's just, again, it's not trick questions, just observation. This is 2 over 1. This is 1 over 2. What do you see it happens? They're flips of each other. And it's not a unique case. That's the general rule of inverses. Why? Okay, what are the graphs of inverses? What are the graphs? So if we had an equation that looked like the square root of x, what would the inverse function look like? Well, yeah, but the reciprocal, the slope changes everywhere. It's symmetric about the line y equals x. So the function and the inverse functions are symmetric about the line y equals x. So let's put this stuff into words. If the slope of y equals f of x at a f of a is f prime, right? That's the slope. And this is not equal to 0. Because if the slope is equal to 0, what does the line look like? What does the line look like? Slope is 0. It looks like what? It's a horizontal line. It's the slope of a constant function. It's not constant. The slope is always constant. It's the same slope throughout. So if the slope of y equals fx at this point is f prime of a, which is not equal to 0, then the slope of its inverse at f of a, remember you switch x and y, is the reciprocal 1 over f prime of a. That's what we're talking about. So if the slope of y equals fx at point a f of a is f prime of a, then the slope of the inverse function at, remember you switch x and y, f of a is the reciprocal of 1 over f of a. That's what we just proved. So the question we have here is this. The derivative of our function, the inverse function within a function, is if we say b is equal to f of a, it makes it easier to see. That means the inverse, the derivative of the inverse at b of b is equal to this. According to what we just talked about there, we have this. That equals the reciprocal So what does that look like? That means it's the derivative of the function so there's our formula. Have we seen this before? I mean, it's just the denominator part. That is the chain rule. Take the derivative of the outside, leave the inside alone. So we have here's this. So our formula, which we're going to be using, is the derivative of the inverse function, f of b, is equal to 1 over the derivative of the original function. So that is our first function, which is called theorem 3. the derivative for inverses. So for this to be true, for theorem 3, it says this. For theorem 3 to exist, we know we have to have two things. One, that first off, for this to be true, the inverse must be differentiable. What does differentiable mean again? Very good. It has to be continuous, limited both sides, so the derivative has to exist at every point in that domain. And the derivative must exist. And last time we talked about if a function is differentiable, it's continuous, then we go backwards. If it's continuous, then it's also differentiable. All right, so let's look at an example here. We'll be using this formula. So the derivative of our function is 1 over the derivative then we'll go with the derivative. So example 1. The function f of x equals x squared for all x's greater than 0 and its inverse square root of x have derivatives f prime of x is equal to 2x and f inverse prime is equal to 1 over 2 radical x. Let's verify the theorem 3. In other words, what we're going to do is try to verify this formula here for the derivative of inverse. So prove that this works. Oop. So what do we know? We know our function f of x is x squared. Check. What is its derivative? What's the derivative of x squared? 2x. We need that because that has to go on the bottom. So the derivative of f is 2x. That's what this part says. Okay, what is our inverse function? Inverse is square root of x. So in place of that, we put 1 over 2 square root of x. And that's it. That's what we just proved. So what that is, that's the derivative of our inverse function. Okay, that's the shortcut method. Let's look at this equation here, and let's do it the way we know already. We know this is using theorem 3. If the inverse is the square root of x, up until now, how would we take a derivative of this function? We would first put it as an exponent. So the derivative of my inverse would be what? The 1/2 comes out in front, and I subtract 1, which is 2 over 2, which is negative 1/2. Negative exponent, x to the power 1/2. Power 1/2 is the square root of x. So that just proves to us that it's going to work no matter what. So we can always go back to the old-fashioned way of changing exponents, or we can just use this formula and it's just automatically going to work. Because all this formula tells us to do is find the derivative of our original function, find the inverse function, and put that inverse function in place of x into our original function. Okay, so we have our derivatives here is 1 over 2 radical x, but that's of the inverse function. If we said x equals 2, what is y? If x equals 2, what is y? 4. That's of our regular function. So now, so we have a point at 2, 4. This is for f of x. For our inverse function, we have to switch those. We have the point 4, 2. If we plugged in the value here, if we plugged in 4 here, what do we get? We get 1 over 2 square root of 4. 2 square root of 4 is 2. 2 times 2 is 4. So the slope of our original function, which was f prime, was 2x. So 2 times 2 is 4. And the inverse function has to be 1/4, the reciprocal of it. So this is where we can test it. Let's see what the next example is going to be. Example 2. Let f of x equals x cubed minus 2, where x is greater than 0. Find the value of the derivative of the inverse at x equals 6. That's f of 2. Without finding the formula for the inverse. It's easier than you think. Because what is this looking for? The derivative is a what? A slope. So we're looking for the slope of the inverse. And how is the slope of the inverse related to the slope of the function? Not negative, just that's a perpendicular. It's just a reciprocal. So if we found the slope of this equation, then to find this one, we just flip it. So what is the derivative of this function? 3x squared. When x equals 6. Actually, we're looking at f of 2. Because this is for the inverse. So we have 3 times 2 squared, 3 times 4, which is 12. Therefore, the derivative of the inverse has to be what? 1 over 12. Very good. So understanding that concept of how they're related makes it much easier. We don't have to do the whole thing. Okay, now we have the derivative of the natural log function. In other words, we're looking at the natural log function is we're going to look at this function here. We'll start off with this. We know that that function is, what do we know about that equation there? What does the graph look like? It's exponential. It never crosses the x-axis, so it's never zero or never negative. It's always increasing. The inverse of this function, which we calculated earlier, is the ln x function. What does that function look like? Because this one crosses that 1 there, this one crosses that 1 there. Okay, so from what we know so far, we know that the derivative of our inverse function is 1 over the derivative of that. So we're going to use this to find the derivative of a natural log. So we start off with, we have to have the f prime. If f of x equals e to the x, what does f prime equal? Nope. E to the x. The derivative of e is e. So the outside is e. So our x value is the inverse function. I'm sorry, this is not the derivative, it's the inverse function. I'm sorry. The inverse of that is ln x. So in place of the inverse part, we put e to the power ln x. According to the rules of exponents, since the bases are the same, what does this become? And there's our answer. It's always, this has to be 1 over x, because if the slope of this one is x, then it has to be the reciprocal of it. Let's take the same one. So our function was f of x was e to the x. And we know that our inverse is ln x. Use implicit differentiation. Remember, what are we trying to prove? We're trying to prove this. So the inverse function, we're saying that y is equal to ln x. And remember, we're only taking it for all the positive x's. There's no negative values. How do we get x by itself? Take the e of everything, right? So we take the e. So we have e to the y is equal to x, because those cancel. Now take a derivative of it, because we're looking for the derivative. What's the derivative? What's the derivative of e to the y? It's e to the y. Since it's a composite, uh, chain rule, we have to take dy dx. The derivative of dx over x is 1. Divide both sides by e to the y. So we have dy dx is equal to 1 over e to the y. What do we know e to the y equals? From step 3, e to the y equals x. So this equals 1 over x. So the derivative of ln x is equal to 1 over x. Because that's what we start off with, taking the derivative of ln x. And that's the general rule. Now, what if instead of x we have an equation? What if we had ln x squared plus 2? So far we know that. But the general rule, if we had an equation there, it's a chain rule. So we take The derivative of ln, which is 1 over the operation, 1 over u, times du dx, the derivative of that operation. This is the general rule of the derivatives of logs or natural logs. So for this example, if this equals y, then y prime would equal, here's the u, so it's 1 over u times du, which is 2x. Here are some examples. Find the derivative of ln 2x. So the derivative of ln is what? 1 over, so this is the x, so it's 1 over 2x. And it's 1 over u du. So this is my u. Times the derivative of u is 2. The 2's cancel, so it's 1 over x. Let's make it 2x squared plus 3. So the derivative of ln is 1 over u, which is 2x plus 3, times the derivative of the inside, which is 4x. And there's my derivative. How about the derivative of absolute value of x? So 1 over absolute value of x. And remember, since we're only dealing with x being greater than 0, what's the derivative of absolute value of x? We did this last time. Because remember, absolute value of x is defined as the square root of x squared. And you can't cancel those. You have to treat them both separately. Look at your notes last time. You'll see that the derivative becomes x over absolute value of x. So looking at this, we have x times 1 is x. Square root of x squared times square root of x squared makes it x squared, which makes it 1 over x. All right. The next example. Find a line with a slope m. Passes through the origin and is tangent to the graph of y equals ln x. What is the value of m? A line with a slope m passes through the origin and is tangent to the graph of. Okay, so let's look at this. The graph of ln x looks like this. It passes through 1. It goes through the origin. It goes through, it has a line y equals x. Or, we don't know the equation just yet. We know what? We know that this point here is A. We know this is f of A, which is ln of A. What's the formula for a slope? y2 minus y1, x2 minus x1. So here's x1, or it passes through 0, 0. So these values are going to be 0. So the first point we have is the origin. And it goes to that point. So on the x-axis, that's A, and this is ln of A. So the slope is equal to ln of A over A. So far, so good? So we know that's the slope. What's the derivative of ln at A? Because the slope is the same thing as y prime. If y is the ln of x, what is y prime? 1 over x. So at point A, it's 1 over A. So we have this is equals to ln A over A equals 1 over A multiply both sides by A. We get ln A equals 1. So what does A equal? What do we do here? How do we get A by itself? E, very good. Take the E to both sides. So we have E to the power ln A is equal to E to the power 1. The E and the ln cancel, so we have A, E to the power 1 is E. So we know this is true. A equals E. So the slope is 1 over E. It's almost time to get out, isn't it? How much time do we have left? I can't see the glare on there. Well, 2 more minutes? Won't be able to finish this. Because the next thing we're going to talk about is the derivatives of general functions of AU and log base A of U. We're going to get those, but we'll do that next time. Have a great spring break, everybody. And see you in a couple of weeks.
Stay safe, thanks.
You too. What's that? I got work to do. What's that?
On spring break.
Yeah, I have tons of work to do. Teachers' works are never done. Okay, everybody, I'll see you all next week.